Hello, today we will continue with the chapter 2 on X-ray diffraction and on Bragg's condition. Okay, so we're gonna review in the beginning Bragg's law, or what is the Bragg's condition, and also we will review the geometrical structure factor, how do we calculate it, and this is very important, remember, for measuring the intensity whenever we are making X-ray diffraction. Okay, let's start. So we decided, or we agreed last time, that the Bragg's condition is found if, for example, here, Bragg, what happened is that if Bragg, he imagined that a crystal is made of parallel planes, okay? And if there is incident beams hitting the planes, they will be reflected with the same angle, okay? And he found out that this distance over here, let me make it in another color to make it clearer. So this distance over here, which he called it the path difference between wave 1 and wave 2, delta, which is 2d sine theta, it must be an integer number multiplied by the wavelength of the beam so as constructive interference will happen. Okay, so this is Bragg's law. And then we discussed the geometrical structure factor, and we found that to calculate it, it is the summation of some number, which happens to be atomic form factor, and this is a quantity that has to do with every scatterer, that is with every atom that scatters, okay, multiplied by e to the minus I rj dot g, and we have used where rj is nothing but xja1 plus yja2 plus zja3, and this is the position of each atom. Okay, if there is only one atom, then I only have one term in the summation. If there is two atoms, then I have two atoms in the summation. And vector G is the reciprocal lattice factor. Okay, V1, V2, V3 can be thought of like HKL, like the Miller indices, HKL. Okay. Now we know that we did the calculation last time, where that G dot Rj is nothing but 2 pi V1xj plus V2yj plus V3zj. Why? Because here we use the fact that Bi times Aj is equal to 2 pi times delta Ij, where delta Ij equal 1 if I equal to j and equal 0 if I is different than j. Okay, in other words, B1A1 is 2 pi, B1A2 is 0. Okay. Okay, and we found that if I put this instead of rj dot g, I find that the scattering factor as a function of V1, V2, V3 is summation over j, that is summation over the atoms I have, fj, this atomic factor, form factor, multiplied by e to the minus I2 pi, V1xj plus V2yj plus V3zj. Okay, and we agreed that the intensity is proportional to the square of the geometrical structure factor. Another thing we did last time is that we calculated these atomic structure factors for BCC lattice and for FCC lattice. And for BCC, we found Sj to be F into 1 plus e to the minus I into V1 plus V2 plus V3, where if V1 plus V2 plus V3 is even, so an example of that, so if they tell me, for example, calculate S of 1, 2, 3, for example, okay, how much is this? So we come and say, okay, here V1 plus V2 plus V3 is 1 plus 2 plus 3, which is 6, implies it will be 2F, okay? However, if I take, for example, S of 1, 1, 1, or they will put it as in Miller indices in this way, Okay, so as of 1, 1, 1, we will say, okay, V1 plus V2 plus V3 is 1 plus 1 plus 1, which is a 3. And if V1 plus V2 plus V3 is odd, I will see nothing. Okay, so in other words, if I do this experiment, wherever I see peaks, they will be the reflections from these planes. Okay, and so in case of a BCC lattice, I will only see peaks when V1 plus V2 plus V3 is even. I will see nothing when V1 plus V2 plus V3 is odd. Okay. As for the BCC, as for the FCC, we found that SG is F into this thing, and we will only see peaks. We will only see peaks. We will see peaks only when all of them are even or all of them are odd. Okay, so again, if I do for an unknown sample and I find that I only see peaks when all the numbers are even or all the odds are odd, implies the lattice I'm dealing with is FCC. Okay, so let's do some exercises. So diffraction condition. So here, X-ray diffraction. Consider a diatomic AB, 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 and this is a one-dimensional object. Okay, so it is AB, 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 with an AB bond length of A over 2. So from B to A, the distance is A over 2. The atomic form factors are FA and FB they have the same atomic form factor F. The incident beam of X-rays is perpendicular to the line of the atoms as in the figure. So it comes this way and gets diffracted this way. It comes this way and gets diffracted this way, making an angle theta over here with the plane. Okay, fine. Part 1, show in details that the diffraction condition is A cosine theta equal n lambda, where theta is the angle between the diffracted beam and the line of atoms, and n is a non-zero integer. Okay, so we have to show this in details. We have to look at this triangle. Okay, we look at this triangle. And we have to remember Bragg's law. So what is Bragg's law? So this is number 1. Bragg's law tells me that the path difference for constructive interference, okay, the path difference, which he called delta, should be equal to n lambda. Okay, so this is Bragg's law, that delta equal n lambda. Okay, now in this drawing, where is the path difference? In this drawing, so this ray and this ray are coming out together. So the path difference is this ray is this line over here. Okay, is this line over here. Let's call it delta. And if I want to calculate this delta, okay, I have this side over here. I have it, it's A, right? This side over here is A over 2 plus A over 2. So this side here is A. Okay, and I have delta and I have theta. Now, in this triangle, it is right at this thing. So let's call this triangle M, N, O. Okay, we should all agree that sine of angle O equal opposite over hypotenuse. Opposite is delta over hypotenuse is A. So delta is equal A sine angle O, right? But how much is angle O? If this thing here is theta and this is 90, how much is this angle? Angle O is nothing but, so delta is equal A sine, angle O is nothing but 90 minus theta. So delta is equal A cosine angle theta. Here I have used the identity cosine pi minus x is equal cosine angle x. Okay, so I use this identity. So I got that delta is equal A cosine theta. So here I will put instead of delta, A cosine of angle theta is equal and lambda. And this is what they are asking me to prove, that A cosine theta is equal to n lambda. I proved it. Okay, so this is part 1. Part 2, find the structure factors S200 and S100 for the reflections S from 200 and 100 planes. So I will start with S200. So here, remember that S will be, here I have 2 atoms. So I have 2 atoms, one at 0, 0, 0, and the other A. So I have B at 0, 0, 0 on this lattice, and I have A at half, it's far by half, 0, 0. So to calculate this S200, I will have 2 factors. So this S200 will be FB, okay, e to the minus e to the minus I 2 pi multiplied by V1, which is 2 in this case. So here I have V1 equal 2, V2 equals 0, V3 equals 0. Okay, so 2, 0, 0 implies V1 equal 2, V2 equals 0, V3 equals 0. So this is multiplied by V1 times the first atom, so times 0, plus V2 times 0, plus V3 times 0. So this from the first atom. Okay, and then I have plus from the second atom, so from F, so from A, FA, and this will be e to the same thing, minus I 2 pi multiplied by V1 times half plus V2 times 0 plus V3 times 0. Okay. And now instead of V1, I will put its value. I don't actually have, so for the first part, this is equal FB e to the minus I 2 pi, V1 times 0 plus V2 times 0 plus V3 times 0. So this is times 0. So the whole thing times 0 plus FA exponential of V2 times 0, V3 times 0, they die out. I have V1 times half times e to the minus I 2 pi, and V1 is 2. So I have e to the minus I 2 pi into V1 is 2 times half. Okay. For the first one, e to the minus e to the 0 is 1, so I have FB plus FA e to the minus I2 pi. Here 2 times half is 1, so e to the minus I2 pi is also 1 because e to the minus I2 pi is 1. So plus FA, but FB, this is equal to FB equal FA equal F. So this is F plus F, and F200 will give me 2F. Okay, so this is S200. Now to calculate S100, I'm gonna do exactly the same. So S100, this means that I have V1 equal 1, V2 equal 0, V3 equal 0, and still I have the two atoms B 0 0 0 and A half 0 0. Okay, so now I have S1 0 0 is from the first atom, it will be 0 0 0 0, so I will get FB, and from the second atom I will get FA e to the minus I 2 pi into 1 times half. 1 times half is half, times 2 is 1. So I will get FA e to the minus I pi. Okay, this is what I will get, and this will give me FB plus FA e to the minus I pi. So remember that e to the I pi is nothing but cosine pi plus I sine pi. Sine pi is 0 and cosine pi is minus 1. So this is FB minus FA. And this is F minus F, which is 0. This means I will get reflection from the plane 2 0 0, but I will get nothing from 1 0 0. Okay. Let's do another exercise. Powder diffraction. So here I have a powder which is made from several scatterers. Okay, so I don't exactly know how much is the D between them. I don't exactly know what is the material I have. Okay, so if the wavelength of an incident beam and the scattering angle are known, then one may easily deduce sorry, the distance between the V1, V2, V3 planes, which is D, responsible for each scattering peak. Okay, so here I did powder diffraction and I calculated all the peaks. So I saw 6 peaks, A, B, C, D, E, F. One happened at D equal 3.157 angstrom, one at 1.931, 1.647, one at 1.366, one at 1.253, etc. Okay, and here remember that the distance, so I got these 4 scattering peaks. The following lines were obtained. So I got these lines. The powder is known to be cubic. Okay, so here, because it's cubic, you need to remember the formula that for cubic, D is equal to A divided by the square root of H square plus K square plus L square. Okay, so we're gonna use this formula, but here we will not call them HKL, we will call them V1, V2, and V3. Okay, so this is the formula for the distance between 2 planes. So we saw scattering from all these planes. Okay, now using the data above, show that, and for the first one, peak A, we found that V1 square plus V2 square plus V3 square is a 3. And we concluded that this is from the plane 1, 1, 1, because if you take 1 square plus 1 square plus 1 square, it gives me 3. So using data from the above table, show that the lattice parameter A is around 5.46 angstrom. Okay, angstrom. Angstrom, by the way, is 10 power minus 10. Okay, and D here is in A, is in angstrom, so I don't have to change units. Now, in order to get this A, I will be using this formula over here. So I will use, so part 1, D, I will put 3.157. It's equal to A, my unknown, divided by the square root of V1 square plus V2 square plus V3 square, which is 3. Okay, implies A is equal 3.157 times square root of 3 square root of 3, and this gives me A equal 5.46. So we solved the first part. Okay, part B, sorry, part 2. Let's do here. Copy and fill in the above table. Deduce the type of cubic Bravais lattice. Okay, so this is a cubic Bravais lattice. So what are the possibilities? It can be simple cubic, BCC, or FCC. But before that, we need to fill in the table. So the easy part here to start filling is V1 square plus V2 square plus V3 square, because we're going to use the formula D. So for each peak, so for example, now for peak B, so B, we will, this is part 2, B, okay? So we're gonna use the fact that the distance is, we want V1 square plus V2 square plus V3 square. So we have D is equal A divided by square root of V1 square plus V2 square plus V3 square, okay? And my unknown is this V1 square plus V2 square plus V3 square. So from this formula, I can get that V1 square plus V2 square plus V3 square is equal to A over D square, because I've squared both sides in order to get rid of the square root. Okay, so peak B, we have, so this is the formula. Now let's start. Peak B, I have D equal 1.931 implies V1 square plus V2 square plus V3 square is equal to A, which is 5.46 divided by 1.931, and we square both sides and we square the whole thing. So we get V1 square plus V2 square plus V3 square equal to 8. Okay, peak C, we have D is equal 1.647. Before I move forward, let me find what are the indices V1, V2, V3 that gives me V1 square plus V2 square plus V3 square equal 8. Okay, here I have to, 8 is what? It is 4 times 2. So if I take, and 4 is 2 square, right? So if I take 220, for example, so here, if I take the plane 220, here I have to think, like do trial and error. If I take 220, so V1 is 2, V2 is 2, and V3 is 0. Now if I take V1 square, this is 4, plus 4 plus 0, this gives me 8. So indeed, V1, V2, V3 equal 220 is correct. Also 202 is correct. And 022 is correct. So I filled this part here. This is 18. Sorry, this is 8. And this is here, I have 200, 202, and 022. Okay, now let's do peak C. Same thing, so peak C, D, I have D, so implies V1 square plus V2 square plus V3 square is equal to 5.46 divided by D, which is 1.647, and I do square for this, implies V1 square plus V2 square plus V3 square is equal to 11. And now, so I found this number here, it's 11. And now what are the indices V1, V2, V3. So as V1 square plus V2 square plus V3 square is 11. Here I have to think of 9 because 9 is close to 11. So if I have 9 plus 2, it gives me 11. So if I take 3, 1, 1 and 1, 3, 1 and 1, 1, 3, all these will give me 9 plus 1 plus 1. It will give me 11. So this is peak D or peak C. Okay. So I have 3, 1, 1, 1, 3, 1, and 1, 1, 3. You need to put here square brackets. Okay. Let's do peak D. Peak D. I have D equal 1.366. So implies V1 square plus V2 square plus V3 square is equal 5.46 divided by 1.366 square implies, of course, here I'm using the calculator, V1 square plus V2 square plus V3 square is equal to 16. Okay, and then what values of V1, V2, and V3 gives me 16? Whose V1 square plus V2 square plus V3 square is 16. So here, if I think of 4, 4, 0, 0, okay, because it is 16, and then 0, 4, 0, and 0, 0, 4. Okay. So here we found this number, 16, and we found these peaks to be 400, 040, and 004. If you do the remaining ones, you will get for E 19, and you will get for F 24, and for 19. So for example, peak E, V1 square plus V2 square plus V3 square equal 19. So what will be V1, V2, V3? 19, you can think of 9. So we can think of a 3, 9 plus 9. So 3, 3, 1, for example, because this will give me 9 plus 9 plus 1. So 3, 3, 1, and 3, 1, 3, and 1, 3, 3. All of these will give me 19. Okay, and the last peak F. So here I have 3, 1, 1, 1, 3, 1, and 1, 1, 3. And finally, peak F, V1 square plus V2 square plus V3 square equal 24. So V1, V2, V3, what would give me 24? If I take 4, 2, 2, or 2, 4, 2, because 4 square is 16 plus 4 plus 4, so this gives me 24, or 2, 2, 4. Okay, so here I got, so I filled the whole table. 4, 2, 2, 2, 4, 2, 2, 2, 4. Okay, so I filled the table. Now deduce the type of the cubic lattice. Notice, when did I get diffraction? Here I have 1, 1, 1. All of them are odd. Here 2, 0, 0, 2, 0, 2, 0, 2, 2, 2. All of them are even. Here, all of them odd. So let me write the notes here. So all odd, all even, all odd, all even, all, odd, and all even. So which lattice, the BCC or the FCC, have scattering when all of them are odd or all of them are even? If you go back up where I made the revision, it is the FCC. Okay, so we notice that diffraction happens when all indices are even or all are odd, implies FCC. Okay, so you have to remember this condition. For the BCC, we should have the summation of V1 plus V2 plus V3 is even or odd. Okay, so you go back up. For the BCC, we found that if the summation of V1 plus V2 plus V3 is even, we have scattering. If the summation is odd, we don't have scattering. Okay, and here it is not correct, because here, for example, I have scattering from 1, 1, 1, which the summation of them is odd. So it is not BCC, and it is FCC. By this, we reach the end of today's lecture. If you have any question regarding anything I mentioned today, just send me an email, and I will be covering it on next lecture. Bye-bye.